Okay, I just opened up the two tabs as I always do for the codebook videos. I open up Google and then I go to the actual codebook website. I went to the codebook website and then I clicked on the last Hamiltonian problem to do, and it just gave me the blank screen of death like it has before. Um, you can see I just went back. I just typed Xanadu codebook and I clicked on it, and yeah, this has happened before. If you remember, the annoying first 5 minutes of another video were about this, so I know how to fix this, but once again, I'm going to lose all of my progress, which is, I guess, not really impactful in some sense because it's all recorded, but it's kind of unfortunate that I have to do this. So I don't know why it does that, but it's very annoying. I could see some people being very sad about this if you've been working on this for a while. I hope that's something that you fix, or maybe it's just because I'm using Edge and it's written for Chrome or Safari or something, but very annoying. Last time we did the approximating exponentials, so this time we're doing linear combination of unitaries. All right, write a circuit for applying a sum of unitaries non-deterministically. All right, so we have UV. All right. So we want to basically create this circuit. So we'll do qnl.control qubit unitary. And we will have U control wires, wires control values. We'll do U control wires equal. I should look at their examples. They always have control wires equals 0, 1, 2. So in this case, we just have 0. We have wires equals 1. Then we have control values. I really do not like this function. It does not seem like the most efficient way to represent this, but that's okay. I will now change this to this setup, so we will have this exact function, right, that we're doing down here. Give an example, complete the code below to apply the sum x plus z to the state 0. You can add, okay, I will do add two unitaries as we did in the last problem. So I'll say u equals qnl.poly x dot matrix, b equals qnl.poly z dot matrix. Wow, this is going good, surprisingly, for once. All right. Okay, what's going on here? Provided the number of unitaries, this happens to be a binary power, select subroutine. So this is select. I've never heard it called this before, but I'm not really in the know with Hamiltonian simulation. The section in the middle, select prepare. Okay, fair enough. So what am I doing? Oh, I see. I am going to go up here, copy this code, and then I'm going to do for u list of index control wires equals 5, 4, 5, 4, 5, and k bits. The wires that the target is on is called in bits, in bits, and then our control values are called control string. K bits. Oh, I misspelled it. Also, I'm going to actually do this out so it's readable on one line. Int object is, oh, right. Oh, that's probably a bad idea. I just want to call bits because we want to offset these. Oh my gosh, write the circuit to apply. Oh, okay, they give us that list. I was going to be sad if. Okay. Okay, so we want to do write a circuit to apply that to the 0, 1 state. So I will first prepare the 0, 1 state. Then I will do select uniform for this new this. Do I need to do anything for this one? Oh, right. This is actually. Check what main is. Range is 2 to 4. Okay. Oh, do we even have to do that? Yeah, we do. What is going on here? Is this not the right? The reason I tried that is because it said that this is equivalent or proportional. I don't know what they mean by that sign there. Yeah, that's what we would expect. Just trying to see. It's so annoying that you can't. There's got to be a way to do it, but I just do not know. It's so annoying that you can't do that. Okay, what is going on here? Oh, why does this keep happening? And as always, every single time, it's always been some sign error or me flipping the order or something, which is very annoying. Write a circuit to apply this, right? U1, which is U list, to this all right, what should it be? This is very yeah, I don't know. I don't know why you would need to access the auxiliary. Oh my god. Why does this always happen? Write a circuit. Okay. Normally it's because I'm misreading. So let's see. Write a circuit to apply. It doesn't even matter what that is, right? XX, ZZ, XZ, CX to the 0, 1 state on the main register. First, let me print. Or here's what we can do. We can just print this. All right, so currently, yeah, it's in the 0, 0 state. So now we will put it into the 0, 1 state. And this is 0, 1, this is 1, 1. This is 1, 0, this is 1, 1. So now it's in the 0, 1 state. Check. So now we want to apply these to the state. Okay, why? Why does it make me do this? Also, why is this not true unless the Hadamars are broken or the select uniform is broken? But it can't be broken because it's right. Oh my god. Okay. Time for the old sketch online. All right. All I'm gonna check is that H we'll do h0 on 0, 1, maps this to, or we can just do h. So this maps this to 0 plus 1, maps this to 0 minus 1. Obviously there's a 1/4 because a constant comes out, so we have 0, 0, minus 0, 1, plus 1, 0, minus 1, 1. So that's the state that we should be getting. And yes, that's exactly what we're getting. Oh, this is actually 1/2, not 1/4. Which means that's exactly, I'm doing the cheating answer, and it's exactly right. Right, yeah, because they said up here, x plus c is equal to h. H of 0 goes to the plus state. Okay, I need to look this up. This is, maybe I should just leave this part open. Because this happens every time. Why? Why does it do this? Let's see. H6, 5, 2, 6, 3. Oh boy. Is it this one? No, it is not. Oh, 6, 3. What is 6, 3 even? What am I even on? I'm on 6, 2. Ah, 6, 2b. Okay, I don't know what's going on, but I'm going to do what I usually do when this happens and brute force it this way. So there's 2. Right. Oh, that's why. End bits is 2, all bits is 4. Sure, we can just do 4i in range. Main box. Okay, I just need to see. Why is this not working? All right, so we have xx, zz, xz, zx. So we can do, oh my gosh. Why does, I think I know what the problem is. I'm going to comment this out, and if this is the problem, I'm going to be very annoyed. Okay, good. It's not the problem. I would have been very annoyed if we have to make the super Oh my gosh. No, it is a problem. I'm annoyed. Oh, okay, that's so annoying. So is this not? This is 1 over square root of 2. This is 1 over square root of 2. This is 1/4. I need to check something. Yeah, this doesn't sum to 1. But that might be because it's entangled with something else. But also, okay, that's very strange, but very annoying. That I thought it was going to do this for us, basically. I didn't realize that we had to do that ourselves. But that's okay. Oh, it's proportional to up to a constant. Okay, that makes sense. Okay. Okay, so we have a more complicated setup. So the first thing we want to do is do unit unitary of b of t equals 0. We're also going to want to do that at the end. You want dot add string with lowercase actually. B of t wires equals 0. Is that how I forget how adjoint works? Let's just try that, see if it errors out. Pop from empty DQ. Okay. Yeah, so I need to look up QML. Oh, there it is. Oh, this should actually be unitary. Is this actually supposed to be? Okay, that's such a weird, a weird format. And then we want to do. Oh, I just scroll up for that. And scroll down for that. So we have u to the first. Oh, okay, so we have u, okay, that looks good. All right, there we go. Because as we see here, the u of 0 is just the identity. Now implement the second order approximation of, right, so now we have this part which we did, and then we have, so, okay. So we have UML dot loopit return v of 2 wires equal box 1 UML dot, just copy this again, u of 2 is that squared. Oh, but we need to put an X on either side of this because we can't specify the X wires equals box 1. And we'll put 1 after this as well. Oh, we don't actually need to put it there. Oh, but that's after the whole. Yeah, we still need to put it there. That's after, so that those ones adjust for this control being open. We need to adjust for this one, which we just did. And then we're going to do the same thing and do this. Make sure this is specified to be 1. We're also going to want see, we're actually going to want t squared. So we're going to want u squared. And now we need to do qml.ctrl. Function control. Okay. Function is subcircuit. The X, the control is 0. Okay, what's going on here? All right, I forgot the V of, this is also a question about that, by the way. I haven't read it yet, but it's worth noting that we still have to do this adjoint operation that I forgot to do before. Wires equals box 1. I actually think we need these T's, to be honest. Didn't have them before. But that's not right. Okay, so let's see. Pretty sure this controlled operation is fine. So we have V, oh, that's right, this is V of T over 2. Okay, so we have V of T over 2, open controlled, oh, that's why this is U2, and this is U1. Okay, that's still not right. U2 controlled wires, oh, that's why. Box of 1, wires is 3. We should do main, I guess, is probably what it's called. Box of 1 and wires main. There we go. And that's still not right. All right, let's go through carefully. Subcircuit aux0, aux1. Okay. So we have our oh yeah, I guess you could just do the transpose of that matrix. In fact, I'm going to copy that. I like that format better. I don't like calling adjoint T/2. It's the same code, so it doesn't matter. But so this is 0, 1, 1 control wires, aux1. Oh, I should adjust that. Oh, we don't actually need to put poly X's here. We only need to put poly X's when we couldn't specify this control value. All right, let's see what this problem was. This is basically, they have a pass there. That's a weird. Et/2. Oh, I'm misunderstanding what control does. Okay, no, I'm not. What's going on here? Right, because this is what I'm doing as well. Oh, and I made the same mistake we actually want. There we go. We don't want the element my square, we want u times u, the matrix square. Excellent. I will now go back. And we are very close. Finally, write circuits which implement the evolution. All right, what am I doing here? Okay, the first approximation we're going to do this first, and we're going to have u. What's the time on this? Oh, u is ml dot rx. X poly x dot matrix times t. We'll do this, we'll do this. Dot x. Let's see, what's the... Oh, maybe it's just 2. I don't think it's -2. No, it's not right. Okay. This is the first approximation, right? First, second. I'm sure these are fine. For the Hamiltonian, we're approximating the x. Is it just times t? You might adjust for that. No, it's not. Also, this isn't labeled, so I don't really know what's what, which is fun. This guy QReg or person is having the same problems that I'm having. What did we do in the first one? I don't even remember. What's going on? What did they say their problem? The circuits from the previous where implement e to tu for u a unitary. Oh, I. Oh my gosh, I didn't even pay attention that there's an I there. So all we have to do is 1j times 1j times. Right. qml.rx. Oh my gosh, I don't want to. I'm gonna open up a Python shell real quick. Deal with this matrix. Penny. I'm just going to Python import NumPy. That's equals NumPy array 0, 1, 0, and then I'm just going to say, let's check how do I do matrix exponential NumPy. That's not what I want. So we want, this is what we want. Okay, so I'm going to go over, I need to shrink this. I'm going to say, first I'm going to import all of these. Then I know you can't see what I'm doing right now. I'm just doing this, but for the X matrix, because I feel like something weird is going on. EXPM 1j times X. So at t equals 0, let's look up the X weight. At t equals 0, we would expect this to be t equals 0. So this is t equal 1 actually. Let's see, this is negative at 1/2. These are both going to be positive. And negative 1/2. These are, yeah, so I think it should be at least negative t. Negative 2 times t. Maybe I was right all along. I should have never doubted myself. Uh-oh. Why did they not just put a matplotlib.label? First order results are red, second order are blue, and full series is green. Okay, there we go. Finish that one. Took a lot of looking up. Oh my gosh, that took 40 minutes. Wow. But we finished it.